Okay, so I'll just do a quick introduction. Welcome everyone to this Institute for Data Science PhD workshop. Okay, first to myself, I'm Jonathan Scarlett. I'm assistant professor in computer science and maths and one of the IDS organization team. So just to say a few words about IDS, we're a very interdisciplinary institute, bringing together sort of researchers from computer science, maths, engineering, and all these different fields relating to data science. We also have partnerships with agencies and industries throughout Singapore. And some of our current main projects and teams include the Grad NUS AI Lab and the AI in Healthcare Grand Challenge. So we have our PhD program, and this week is about having our PhD students share some of the knowledge that they've learned. So this is to, first of all, give our students the experience in sort of, learning how to teach and interact and so on, and also develop their own knowledge so that they can teach it. And of course, it's also for the attendees to be able to learn and promote some interactions, help share the knowledge that's been accumulated, and so on. So yeah, today's will be a one-day workshop given by Guilherme on scientific machine learning and also the Julia programming language. And so with that, I think we can begin.
Right, and thank you for the introduction, Jonathan. I will conduct the workshop. There will be like I will try to give 1 hour talk, and then we'll give a break, and then we resume. Then I'll make a pause for lunch, and then after lunch we go back, and then we complete the workshop in the afternoon. So if at any time you have any questions, please feel free to write them in the chat. If you can write to everyone, or if you have anything that you would like to share just with me, you can just send a message directly to me. I will try to keep an eye on the chat, but sometimes it can be a bit hard with so many screens around. Okay, with all that being things, with all that being explained, let me start the workshop. So the objective of the workshop is to, as Jonathan said, is an introduction to scientific machine learning. So I'll try to guide you through like this universe of scientific machine learning. It will serve as an introduction, and I hope that I can give you enough pointers such that if you are interested in the topic, you can continue after on your own. So the outline of the talk today, I'll give you a motivation, then I'll give you an introduction to Julia. There will be a debug session. So somebody asked if there will be a debug session after the motivation, and before we start coding with Julia, I will make sure that everybody has Julia installed, or if there's any issues, we can talk about it. So I'll reserve like 20 minutes to do that. So then I'll discuss ODs with Julia. Then after I will approach neuro ODs. Is talk about the universal differential equations, sparse identification. Then topic number 7 maybe is a bit more mathematically heavy. So anybody who is not so interested in the math doesn't need to stay. But I will talk about what we are doing behind the scenes with ODs and neuro ODs, and then I will conclude. So I'll start with the motivation. So first of all, like as Jonathan said, I'm a PhD student at IDS. So my work basically consisting in studying empirical temporal networks and understanding how things diffuse through networks. So when you're talking about diffusion, we're usually talking about like differential equations. And so I've spent a good part of my second year studying how differential equations work, and then Julia was an important tool in doing that. So I'll just maybe show you a little video about the work that we're doing, so like that we know the kind of so you understand the kind of work that we do at the lab. So share some. So let's see. So let me open this directly in YouTube so that. So yeah, this is a little trailer of our work. There's a full-length version in YouTube. I can share with you after if you're interested. And at the end of it, maybe you saw a simulator. So there's kind of things that we can do with ordinary differential equations. So like we can simulate diseases and understand maybe how it propagates through the student population at NUS. Okay. So the three goals for the workshop. So the first one is to have a basic understanding of what an ordinary differential equation is. I'm talking here from a math perspective. Then we will be able to formulate an ODE problem and understand how you can find solutions for a given set of parameters and estimate it using Julia. Then we will learn the basics of scientific machine learning. So in particular, I will focus on these libraries from Julia. So it's differential equations, diff equiflux, and these other three. So the main one is the differential equation is the workhorse for ODEs in Julia. Okay. And so what is an ordinary differential equation like? So maybe like more philosophically speaking, like we're trying to do is we have a dynamical system that is evolving through time, and then basically we can observe a set of states at each point in time. So it's as if like you filming something, and then you can keep track of the time, and then each picture of the movie represents a state. So basically you have a mapping from a given period to what you observe. So the objective of ODEs is to describe this mathematically. So to describe how you go from state, let's say at 10 seconds, how the state moves to 11 seconds. And then if the system is simple, you can describe that with mathematical equations. This discipline started with Henri Poincaré, who developed an extensive theory of dynamical systems and of sciences, and basically like try to understand what do we mean by cause and effect when things are changing simultaneously. So the most basic one of the most basic ODEs is comes from physics, and this is the physics. This is the harmonic oscillator. So basically, like we can describe the movement of a weight that is suspended by a spring. So as illustrated here in this picture, according to the law of motion. So the law of motion says that there is a force, and the force equals mass times acceleration. And we can express acceleration as the change of the velocity in time. So this will be like d square x dt square, and that is equal to. So we have a description for the force which is equal to minus kx. So like the way that the force operates on this object is according to a constant, and it decelerates it with the proportion k, and then the m here comes from the law F equals ma. So in fact, this equation here represents a system of differential equations, because you have a law for the velocity. So velocity is expressed as the change of the position in time. So again, if you have the image of the move in your head, you see an object at position 10, you see an object at a certain position, then you move forward, you see the object in a little bit forward, and then as you move the time, you see the object moving forward. So this is what the velocity represents. And then the acceleration is how the velocity changes with time. So, and then this is what we had. And in fact, we can represent the system using Julia. And don't worry about the notation, the coding. It is just an illustration, and now we're gonna cover that later in the workshop. So as I showed to you before, there was the equation. The system of differential equation is represented by this, and then here we have the same system of differential equations represented in terms of code. So here's the velocity, and then here is the acceleration. And then we can solve the system and basically plot. And then you see that when a mass is influenced by a spring, you have a cyclical movement. So it goes up and down, up and down, up and down. In another field that we have is in another field of science, we have in ecology we have a system called Stochastic, and this system of equations we're going to explore in a lot of details during this course. So basically, it says that imagine there are two competing species in the environment, and then in this case we have the fox and the rabbits, and fox eats rabbits, and then rabbits so you have the rabbits are born with a rate alpha, and then they are killed by the fox at a rate beta. So the rate at which rabbits die, it's equal to the amount of rabbits, the density of rabbits in the population, and the density of fox. So if there's a lot of fox, there will be a lot of dead rabbits. And then if there is also a lot of rabbits, it's easier for a fox to find a rabbit. So it will also be able to kill a lot of rabbits. On the other hand, the foxes are born at the rate which they can, at the rate that they can eat rabbits. So they need to eat rabbits to function, and then they are born at the rate that they're able to hunt. On the other hand, the fox, they don't have any predator in the system, and so they just die naturally with the rate gamma. So again, we represent this system using Julia. Here, we define a function called Lotka-Volterra, and then here we extract out the parameters of the equation, and then equation 1, you see the first equation above, and then in equation 2 you see the second equation. Again, the solution of the system is a periodical. There's a cycle. So fox as fox become large, they kill a lot of rabbits, and so they start dying because there's not enough rabbits. And then as the number of fox decrease in the environments, the number of rabbits increase, because now there are not enough fox to hunt them. And then as the number of rabbits increase, there's a lot of food available for the foxes, and so the rabbits start decreasing again. And then this game of cat and mouse goes on forever. So I'm just demonstrating some examples from the different fields of science where ordinary systems of equations are used. So if you have any questions, feel free to stop. Another field that we use ODs is in epidemiology, and then maybe in the beginning of the epidemics, there was a lot of there's a lot of discussion about how infections are rising and how many people are getting recovered. and you might have seen a lot of curves like this showing in the media. So I think there was a lot of discussion about like herding effects, like when are we going to get out of the epidemics. So this can the dynamics of an epidemics very simplistically can be described by the susceptible, infected, recovered model. So you start with a population that's fully susceptible, and then and then somebody gets infected. So once somebody gets infected, like the rate at which a susceptible becomes infected is equal to the proportion of infected in the population times the rate of infection beta. And then if we compare to the Lotka-Volterra equation, this is in a sense very similar to how the prey-predator dynamics work. So in a sense, we can think a little bit. We can think that the infected are preying on the susceptible, and then the susceptible are like becoming infected at this rate beta, and then the infected because for every susceptible that becomes infected, it's a 1-to-1 mapping. So then the number of infected increase at the same rate as the number of susceptible dies. And then you have like the infected. Yeah. So do we need to first have the equations crafted out? So not necessarily, like so we'll see in later parts of the course that it's not necessary. We don't really need to have the equations crafted out before, but having some knowledge of the system definitely helps when you're modeling something. So I guess this goes back to what we have in machine learning, the overfitting. So if you don't have any information about the system and you just try to fit, like let's say a neural network to the data, you might get a model that fits very well to your training data, but when you extrapolate to the testing data, it doesn't fit so well. And so like so we'll discuss the trade-offs between having a system, a well-defined system, and using like starting from a neural network. So in this case here again we have the susceptible, the SIR model. We can describe it using the function here, and then we can solve it, and then we find it. But notice that for every solution we have to state what the parameters are. So a solution, when we're talking about ordinary differential equations, a solution is the trajectory of the system. So it's not one point or anything, it's the full trajectory. So if the system is under certain laws and then we have certain parameters, our solution will be this trajectory. And the systems of differential equations are usually very sensitive to the parameters. So if you change the parameters a little bit, sometimes the solution can be completely different. And then in economics, so this is the last example, we have a model for growth called the solo growth model. And in this model, we have that the production function describes how the inputs are used to produce goods and services. So you have that that economic growth is a function of capital per capita, and then the capital the capital disappears from the economy at the rate that it depreciates, so delta, at the rate that technology grows, and at the rate that the population grows. So because we're talking about capital per capita, if you have more people and the same amount of capital, then your capital will decrease relative to the number of people. And basically the law of motion then is equal to how much capital, the law of motion for capital is equal to how much capital you save from your output minus how much capital disappears from the economy. And so in most cases, in a simplified model, your production function will be Cobb-Douglas. So basically, is a concave function that's equal to k to the power of alpha. And alpha is usually equal in a competitive market. You can prove that the rate alpha is equal to the return of the capital. So what economists are after then is to know what's the steady state of the economy, and then usually the steady state will be equal to the point where the savings equal the depreciation. So here in this model, you'll see that the depreciation is linear, whereas the production function is concave. So you see that as the output grows, as the capital grows and becomes at a decreasing marginal rate, whereas the depreciation increases at a linear rate, there will be a point where there's a steady state. So for every capital you gain, it depreciates. And then on the left side, we see the amount of capital that the capital reaches the steady state. So these are all examples that I gathered for today, but this is only to illustrate. There's many more examples that in the literature. If you're talking about, if you're looking into molecular biology, there's a lot of models about how cells and there's a lot of models to model this cell and how proteins are manufactured in cells and all that. So it's not quite my area of specialty, but there's models for that. Also, if you look into climate modeling, there's a lot of differential equations there. So basically, every field of science will have some differential equation. So as you might have noticed, there's a common thread in all of the presented models. So the variable of interest usually changes a function of time when a given set of parameters are held fixed. So if I say so our variables of interest throughout this workshop, they will be represented with the variable u, and you can have m number of variables. So for instance, in the SIR model, we have 3 variables. In the solo growth model, we have 1 variable. And so this will be represented by the vector u. And then we also always going to have a law of motion. So the law of motion is any function, any function that you can think of that will map your states now to your states a period later. So that's why the function goes from the set of from Rm to Rm, because it has to map to the same set of the domain. And so in a very succinct form, we can write our differential equation as du dt equals fu. And every single model that I presented above is an example of this generalization. So when we're talking about the solution for the ODE, what we're after is we would like to know what function u gives rise to this law of motion. So if you give me a set of initial parameters and an initial condition, how will the system evolves? And then it might be surprising or not, but then if you have a single law, if you have a law of motion, then there is only one function that satisfies that. There's only one trajectory that's possible. So it's a little bit like saying if you walk in a straight line, you know where you're gonna be a few periods later. Okay. So far when I'm talking about the generalization, we place no restrictions on the law of motion. So far we have placed, so in practical terms, I'm saying like if our system, let's say U is in a given state D, I could say the next time period the system will go to D. But if the system is in A, then the next period it will go to C. Also, if the system is in C, it will go to C. So we could describe our system basically using just an enumeration of all the possible states and then mapping one state from another. That might sound quite simplistic, but it is actually a common way of describing changes using Markov chains. So in a probabilistic environment, and there are extensions of ODEs to stochastic systems of differential equations. So that's why like this simple example here is actually quite common. So if you want to generalize, because like just listing a number of states and mappings between states is not very generalizable. We could think about other strategies for building our law of motion. So one simple strategy is to say like our law of motion is a linear function. So what do we mean by when we say it's a linear function? We're basically saying that my state, the state tomorrow, will be change the changes. Sorry. So what I'm saying is that like change happens in proportion to the current state. So it's a little bit like you put your money in your bank account, and then now you have $100, and the bank pays you an interest of 10%. So your state the next day, so there's a very high interest rate, 10% per day. So your state tomorrow will be 110. So as you can see, the law of motion is proportional to the current state. So because it's 100 times 1.1. So that's what I mean by being proportional. And all of this type of laws can be described as a linear function. So the simple harmonic oscillator in the beginning of the workshop is a member of this class of functions. So this can describe many simple phenomena using just a simple linear algebra. Then if we expand our horizons, and now we come to I think there was some question about that. What kind of functions can we use? Do we need to know the functions? So the answer is yes and no. Like so we could use neural networks. And neural networks basically, you're basically saying I don't know what function it is. It's a function that has many parameters. It's represented by a neural network, and we know from the literature that it has been proven that a neural network basically can approximate any function that we can think of, any well-behaved function. And there's different versions of this theorem called the universal approximation theorem that shows that under certain conditions, which involves many general functions, we can approximate that with a neural network. So in a sense, it's good because we can say, I don't know what function I have. I know that it can be represented by a neural network, and I know that a neural network has like a very large number of parameters. So if I want to fit my data to this, then I can basically try to find the optimal set of parameters for my neural network. So in a sense, like we're not, so if you use a neural network, we're not using the most sparse and concise law of motion. But you can think about the neural network as a surrogate model of the true model. And in science, I think we're always looking for simple models, because not only because we want to avoid overfitting, but when we're trying to fit a model to the data, we're not only trying to fit to that data set, but we're also trying to make sure that it's generalizable and that our theory fits with everything that has been built around it. So how the planets gravitate around So how the planets interact with the law of motion for the planets have to be in agreement with other physical laws. And then if we use a neural network, it's very difficult to like put all these things together in a simple, in a comprehensive system. In any case, then the other advantages of the neural network is that it overcomes the curse of dimensionality. So what do I mean by that? Is that like, so if you're trying to model your function using a polynomial, so you have x1. So let's say you have just two variables, x1, x2. You want to model the law of motion. You can have x1 be a function of x1 plus x2 plus x1 times x2. And then let's say you want to have a square, then you'd have x1, x2, x1, x2, x1 square, x2 square, x1 square, x2, x2 square, x2. I don't have a, I wish I could write, I didn't prepare myself for that, but maybe after the break I can figure out a way of like writing stuff now. So in any case, if you're using polynomials, you can see the number of terms just grows very large, very quickly, and that's what I mean by saying that that we have t, so the number of dimensions of our model time to the power of m. Whereas if you're using a neural network, because we have a fixed depth and a fixed width, our neural and that fixed depth and fixed width can approximate the function with a certain precision. Any function with a certain precision given a depth and a width. That means that our number of parameters is basically fixed. Although it's very high, it's fixed. Whereas if you're using a polynomial, it can be arbitrarily large. And this is particularly important when you're modeling like fluid dynamics and all that, because when you're modeling fluids, you can have a state is basically the state of every single position in your fluid. So you can have like very large systems. So neural networks also are good because they enforce many arbitrary constraints. So what do I mean by that? Let's say our system can only have positive states. So if you're talking about biological, ecological systems, you cannot have a negative number of fox. You cannot have a negative number of rabbits. And with the neural network, we can basically enforce that every variable is positive by using, let's say, an activation function that's equal to the square, or you can use an activation function like the ReLU that makes sure that everything's either 0 or positive. Then the first point is that the neural networks are isotropic, so they are naturally non-aligned to a basis. So what I mean by that is that you could approximate functions using like sines and cosines, like especially functions that are cyclical, but that imposes a very strong constraint on the functions. So it basically has to be cyclical, and it has to and you basically composing like a multiple number of cycles that have a certain width apart. So when using neural networks, we don't need to impose any type of constraints about like what's the width of the cycle and all of that. And so like if you want to, for instance, approximate a non-cyclical function with sines and cosines, you have to use a lot of many very large number of functions from the class of sines and cosines. So from very low frequencies to very high frequencies. Whereas with neural networks, because it's not aligned to a basis, this is not required. And finally, neural networks usually both they can reach the global minimum more easily than other types of optimizations. But as we're gonna see later on, this doesn't always happen in practice. So okay, so I'm saying that, so maybe you have a data set and you say, okay, like I have my data set, it tells me what's the number of fox and rabbits for each period of time. So why do I want to use a law of motion? Like maybe I could just approximate this data set straight using a neural network. So why do I have to bother about modeling the law of motion for them to figure out what's the solution? Why don't I just go and model the solution? So first of all, like ODs usually don't have an analytical solution. So even though so all of the models that I showed you, most of them cannot be expressed using like using a closed form as a solution. So something like x equals 2x. And actually, like all the solutions are found through numerical approximation. So that's why we use ODs, because it basically describes what we're observing. That's how things are changing. And for this reason, and then apart from that, we usually use neural networks inside of models that we partially know about. So if you have an SIR model, we know if we're going to try to model the COVID epidemics using neural networks, it might be a bad idea to just use a neural network out of the box, because there's so many moving things, and because the disease is growing exponentially, and then it reaches a plateau and then changes again. If you just use a neural network, you're just going to fit to what you observe, and then a couple of weeks later, COVID will change, it will evolve, and then everything in your model will be very bad. So what you can do is, like, you can actually add, you can actually write your system in terms of what you know, and then add the neural network for modeling what you don't know. And then you can do that if you model in terms of an OD, you can very naturally add both things together. However, it's possible to do what I just described, and then you can see an example just by following the link that I posted. So I kind of like the quotes by a very prominent developer in the field. He says that so if a picture is worth 1,000 words, then a model is worth 1,000 data sets. So no matter how much data you have, like what's more important is actually that you know what's happening, like that you have an explanation for the phenomena, and that it doesn't matter how much data you have. If you don't develop an explanation, you're never going to know if your model is going to fit the next data point. So I can trace an analogy to the black swan. So in Europe, they thought there was only white swans, and so you could say that the law is that swans are born white. And then when they discovered Australia, they eventually found the black swan. And then the law, and then if you just base your explanation on the data, then you think that there's only white swans. But then if you understand a little bit of genetics and how things could, and how the color of the swan, I mean, I'm not a specialist, so maybe it has nothing to do with genetics, but hypothetically, if you think that the color of the swans related to genetics, and you have a model for how this thing work, then it could potentially say that it's possible that the black swan exists, even though you've never seen a black swan. And so that's a little bit what we're trying to do here, is like to learn models from data, but in a smart way that will allow us to generalize from it. So I would like us to make another detour, like so I talk a lot about dynamics and how things change, like in a deterministic way. So you might ask yourself, like, what about stochastic models? Like maybe I don't know how things change, and I could model this as in terms of probability. So if I film something, and I see that a certain percentage of the time the model is in a state, another percentage of time the model is in another state, and then I could potentially model the whole system using a Markov chain, as I described before. So why don't we just do that and forget about dynamical systems? So yeah, that's a possibility, especially when the system is very complex and we don't know much about it. So before we dive into discussion of that, I would like to illustrate this problem with this video from about how to flip a coin. So
there it is. That's hard.
So let me put this sound. Okay.
It's hard to get. I don't know if your camera is fast enough to catch that.
So let me, if you cannot see, just write in the chat.
There you go. So for many people, me in particular, viscerally, this is as close to a random phenomena as I know. And yet, you can think about it. If you knew when the coin leaves your thumb, if you knew how fast it was traveling, and if you knew how many times a second it was turning over, Newton tells you, if you know the speed, how long it takes to come down, and then if you know how fast it's turning, you know whether it'll come up heads or tails. Coin tossing is a deterministic process. You know, what's random about it? First of all, let's try doing a little of the math of tossing a coin. I'm going to say feet per second. I know that's unpopular. And here's revolutions per second. So a dot on this plane is a coin toss, right? A dot on this plane is how fast it's going and how many times a second is it turning. So for example, a dot here near the axis, so the speed is high, but the revolutions per second is not so much. So that means it's going up like a pizza. You know, it's kind of doing this and not really turning over. If it's close enough, it might be just, you know, kind of slowly turning. So it might be that it doesn't turn over at all. Similarly, a dot here, very near the axis up here, is a coin which was thrown with a lot of revolutions per second, but very low speed, so it never gets very far. So there's a region like this of initial conditions where the coin never turns over at all. Okay, any place in here, the coin never turns over at all. There's some region, and we could figure out what this curve is just, you know, it's first course in physics. And then there's a region where the coin turns over once. You know, initial conditions here, the coin just turns over once. And then there's a third region where the coin turns over twice. And then there's a fourth region where the coin doesn't, you know, turns over 3 times, which is the same as turning over once. And these regions alternate. When you do the math, what you find is these regions get closer and closer together, so that small changes in initial conditions make for the difference between heads and tails. And for most of us, that's what makes coin tossing random. Now, you can ask, when real people flip real coins, where are we on this picture? I want to know, how fast is the coin going when it leaves my hand? Is it going 5 miles an hour? Is it going 20 miles an hour? Is it going 40 miles an hour? It makes a difference. And so I got a friend with a stopwatch, and I went 1, 2, 3, flip, 1, 2, 3, flip. And we got sort of synchronized, and so he could tell how long it took the coin to come down, and from that I could tell how fast it was going. Now, it took 3 hours to get that data, if you think about it. Okay, to get the data about how fast is the coin turning, I had a good research idea, which is the following. I took a coin and I took a piece of dental floss, you know, the tape type dental floss, with about 3 feet long, like that. And then I flipped the coin up, and then I could unwind the dental floss to see how many times it had turned until it was flat again. The floss twists around, and now it's true that a coin flipping in the air with a piece of dental floss is different than a coin just flipping in the air unimpeded. So, as with any measurement process, the measuring interferes with the randomness, but okay, you hope it's a third order effect. Based on those kinds of experiments, and a lot more of that, I know where we are on this picture. And what was funny is how fast the coins go. A typical coin flip lasts about half a second. And when you translate that, that means the coin's going up and back about 5.5 miles an hour. That's how fast this coin is traveling. and now I have to say where we are on this picture. This dot, where we are in this picture is about 5, and this is 1, and in the units of this picture, 5.5 miles an hour comes down to very, very close to 0. But the revolutions per second were 40 units up in the picture. So this picture says nothing about real coins, but the math behind the picture tells you how serrated you are up there where you can't see.
Right.
And it seems to be true that coins, the way when we flip them, are fair to 2 decimal places, but not to 3. It's not perfectly 50-50, right? In work with Susan Holmes and Richard Montgomery, we showed that coins, the way real people flip them, it's about 0.51, so 1 in 100 off, and it's not 0.51 to heads or tails, it's 0.51 that it comes up the way it started. That is, if you started heads up, it spends more time heads up. It's just, and there's this, and I don't care how hard you flip the coin. You can flip it to the moon. That bias is it's a provable, stable bias, and it's again not a, I think, or from experiments. This is, it's a theorem. When real coins flip, when we get your high-speed camera, you'll be able to see that they don't turn through their axis of symmetry in that way. Through this plane, they precess, and they do pretty complicated things. And because of the precession, it's not just a simple, 2-parameter business. The real analysis of flipping a coin, it's 12 parameters. Actually describing a moving coin is a 12-dimensional problem. It's not something I can draw a picture of. We did the analysis in the 12-dimensional space and put in some data from real people flipping real coins. We had to measure the distribution of angular momentum when real people flip real coins, and that was quite challenging, but we did it. And so based on all of that analysis, when you flip a coin, it's about 0.51 to come up the way it started. So it's better if you see its heads, it's better to guess heads. It is also true that if you take a coin out of your pocket or jiggle it in your hands, that probably makes the start random. And then physically flipping a coin won't destroy that randomness. It's not as if the coins have a predilection to kind of favor heads when they come.
This video. Okay, so the reason I showed you this video is like to contrast to kind of like bring you the perspective like between the difference of like dynamical, between modeling a system as a dynamical system and modeling it using stochastic processes, and I think that the whole idea is that like, okay, if you're flipping a coin, like you know that the coin is gonna end up in either of 2 states or heads or tails. So you can model this using a Bernoulli distribution, and that. But as we saw in the movie, but the real thing, the real problem here is we know that because we know that the flip of a coin is sensitive to the initial conditions. So if we change the way that the coin starts, the way that we start flipping the coin, because the interval between when the coin is going to land heads or tails is so small that that if we don't know the exact parameters and we cannot measure it very, very accurately, then the flip of a coin is as good as random. But like now, let's imagine that we have a very complex scenario, and there is not only heads or tails, but there is like maybe hundreds of different dimensions of the state. If you model this using a stochastic process, you might be only narrowing your field of vision to a very particular place in the set of states, and you're not gonna be able to have the big picture and really understand like how my system is sensitive to the initial conditions, what are the possible initial conditions, if I start my system from a certain condition, what are the where it's gonna end up? Does it always end up in the same place? Does it end up in only a certain number of different places? So for that, you need to have like an understanding of how dynamical systems evolve. And that if you then discover that this dynamical system maybe is very sensitive to initial conditions, and the initial conditions are kind of like uniformly distributed, then you can maybe model it as a stochastic process. So you can do both. So you can model a system. So it's always about parsimony, and it's about generating insights. So you could use a dynamical systems if you don't know really what's going on, and you have a certain ideas about the laws of motion. But if you can only observe, if you can only count the frequency that the system ends in certain states, and then and the system is too complex, you could use like a stochastic process to model it. Okay. So summarizing, like the idea of using models then is that we would like to understand what the simple laws that drive the whole system's evolution. So in science, like it's not enough only to have access to data, but we really need to have access to theory. And the idea of scientific machine learning is then to develop theories based on the data that we observe. And in most cases, the data only tells part of the story, and you as a scientist, you have to come up with the other part. And machine learning, what machine learning is bringing to the table is allowing scientists to use a very large data set with many different dimensions and guide that process of discovering new models from that data. So that involves like drug discovery, that involves modeling fluid dynamics, and many other applications. So now we have reached the end of the motivation section. So maybe you have any questions or any thoughts about the workshop so far, or any expectations of what you would like to see. Maybe now it's a good time for you to share your thoughts. So you can either write in the chat, or maybe you can unmute yourself and ask a question, or maybe make a comment. We can make it more interactive. So, right. So I guess okay. So if nobody has any questions or comments, maybe later you have the motivation was maybe a bit more philosophical, or and then we're gonna get now to the nitty-gritty of modeling, and I guess a lot of people a lot of you interested in Julia now that. So why don't I give a break? So 5 minutes break, and then you can take a cup of coffee, or you can take a break, and then we come back at 10:05. Okay. Okay, thanks. So I see you in 5 minutes then. Okay, everybody. So I'll continue. Hope everybody had a good break. So we start now an introduction to Julia. Maybe you can write in the chat. Does anybody have experience with Julia before? I don't know if it's gonna be too basic or not. So maybe let me know. I'd like to know if everybody has seen Julia before, or if it's your first time. So I think we're only only 12 people. Maybe you can write if you know Julia very well already, and then I can have an idea of like where we are. So maybe if you don't want to share with everybody, you can write directly to me or something, then I can have an idea. So okay. So anybody else? Maybe video. So I'm gonna, I guess, assume that then nobody has had experience with Julia like before, like since right then. So let me then start to the introduction. So Julia is a programming language for that's used a lot in scientific reasons. It kind of like replaces, or not replaces, but it kind of like brings a lot of good things from different languages into a single language. So it brings the speed of C and MATLAB. It brings like the dispatch from R, and then it also brings the user friendly in the community from Python, but the community also from R and all the other languages. So this actually comes from the website. So Julia is best because it's a just-in-time compiled code. So that means that like Python is an interpreted code, so you have like a C I think compiler, so you write your code in Python and it runs automatically because it basically sends the code to like a process that executes the code and gives you back the result. Whereas like with Julia, you need to compile that code, and then that code then becomes machine language code, and then it executes natively in your computer. So the first time to plot it's slow, but then after you compile the code, then it's very fast. I think like a very nice thing about Julia that I haven't seen any other language that I've used before, and I think that's it's a big advantage of it is that it's by its nature it has a reproducible environment. So it's not like Python that you need to choose Conda or that you need to choose like package managers, or like R that is a big mess, and then every time you upgrade R you have to kind of download all your new packages. Julia is by design built with a project manager, and so it's very easy to first install different packages and switch between different environments. So with Python, for instance, if you switch between different environments, you basically have to reinstall every single library. So if you start a new common environment, you're gonna install everything again, and it adds up and takes a lot of space in your computer. But with Julia, no, like with every single package, every single version gets an ID, and then everything gets stored in a centralized location in your system. And every time you switch to a different environment, it basically just uses the libraries that comes from the central location. And then it becomes very easy to develop code. So maybe I can show later. If you're developing, if you want to change something from a package, just for playing and just for like fun, you can go and change it very easily. And then after you're done with your experimentation, you're not satisfied, you can go back to the original one. And then I think this is like completely revolutionized the way you interact with code. So Julia is general. You can go from basically system input-output operations to data wrangling and data analytics and data reporting. So you can do basically everything you can do with Python, you can do with Julia, which is not so much the case for MATLAB and R, which are specifically built for scientific purpose. But Julia is in a sense a bit much more general and much more closer to Python in that sense. So Julia is so I say it's dynamic, so it feels like Python. So okay, the first time you plot something, or the first time you load the library, it's gonna feel slow. But after you load it and it has compiled, it's very fast, it's very dynamic, and you can use it to be like Py. So it's composable. So in that sense, it's not like Python, because rather than use classes and objects, you're using like a different paradigm called multiple dispatch. So you can write a function, and then if you pass an object of a certain type, it knows what to do, so it dispatches to that object. So if you are familiar with Java, you can define a function and then you do something different depending on the object that you pass to it. And this is very similar also to R, if you have had experience programming in R. And finally, Julia, like many other programming languages, is open source, it's MIT license, and most importantly, it's developed by a very active community of scientists, computer scientists. And actually, like if you go to Discourse is where you can look for help. So Stack Overflow is not so popular with Julia, so if you find less questions there, but in Julia Discourse there's a lot of information. So right now they're having the Julia Conference 2021. There's a lot of nice tutorials, a lot of very nice discussions there, and you can learn a lot. But if you're interested in dynamic equations, you basically want to search for things with the tag diff-eq. So if you click, so if you search for it, you find a lot of like interesting questions. You can learn a lot from people's discussion, and I actually do this all the time. I go here and I just like read random questions, and I usually learn. And finally, like Julia's website is where you get started, and then you find a lot of resources. So what makes this language special is the amount of packages that have been developed and are in active development for the purpose of machine learning, scientific machine learning, for mathematics. And here is just an illustration of some of the packages. So differential equations is really the workhorse, and Julia, for many people, Julia became famous because of this set of packages. It makes it very easy to write differential equations, to solve them. It feels like you're writing maths, not that you're writing code. And then like I think that's what drove me in the first place to Julia. Now there's other packages for function approximation, manipulation. So we're gonna see a little bit of the data-driven diff equation. The jump is a package for modeling. I'm not very familiar with, but there's a talk in Julia conference. You should watch it. This seems to be like a very popular package in the community. There's also packages for operating with CUDA GPUs. So like Python, Python has a very strong support for GPUs. In Julia, you also have a lot of packages for GPUs, and they are. The nice thing about Julia is everything is written in Julia. So as opposed to Python and R, when usually you write a wrapper that then executes a function that's written in C. So that's how NumPy works. Whereas in Julia, like everything is defined in Julia. So if you want to know how the square is how the plus squares basic functions are written, you can go and check in the package how they're doing. If you want to see how a push operation is defined, this is defined in Julia. And so CUDA and CUARrays, they are like GPU. They are libraries for writing code for the GPU operations for the GPUs, and so you can use Julia to write, and they provide a lot of the APIs. I watched a tutorial last week about how to use CUDA with Julia, and I think it's very promising and can make a lot of can make it very easy to port code to the GPU. So another thing about Julia is the automatic differentiation. So you have libraries Zagatti, forward diff. Now there's a new one coming up, I think called Enzyme. Basically, they are doing they are libraries for automatic differentiation. So you define a function and then it knows how to differentiate it. The author Chris Rakaukas has a very good course in MIT about numerical programming, and a couple of lectures are only about automatic differentiation and how these things are implemented in Julia. So I recommend this course here. And then you'll find a lot of the information about the automatic differentiation in lecture 8, and lecture 8 and lecture 10. So I highly recommend. And finally, if you're doing neural networks, you have Flux, which is basically the TensorFlow, the PyTorch of Julia. And again, like Flux, Flux is a neural network library, and everything there is written in Julia. So it's very easy to contribute. It's not like maybe if you're programming for TensorFlow, like if you're developing new layers or new things, maybe sometimes you have to use the APIs provided by the package. But with Julia, like basically like the whole environment is a possibility. Okay. So now that's where you go. Now we talk about the installation, then I'll pause, and then we can debug and answer people's questions, and I'll help people getting it set up. Since we are not many people, like I think it's doable. So to follow the course, please go to the official page. Julia's official page. You download the Julia version for your computer. So in my case, it's for Linux, so I downloaded the 64-bit here. Then I just follow the instructions. If you're using Mac, you can download directly from here, or you can use the Brewcask, and then just Brewcask install Julia, and then you have a working version of Julia. And for Windows as well here. So after you do that, then you clone my repository, the repository for the course. So that's based in GitHub. So it's this one. So you just download everything. You just clone the repository, and so I just follow. I'll just do it. I just do an example in Jupyter here. So if I start a terminal, so you can see my screen, the terminal. Okay. So let's say so I go to downloads. So I'm in downloads here. So I just git clone my repository. Okay. And okay, then it opens up a page here, folder. So I change to it. So now I'm in the new I'm in my repository here. Then I just start Julia. So you want to press the right side bracket in your keyboard. So is this this character here? You just press it, and then you're gonna be in the package environment, in the package mode of the interpreter. So here, if I type status, you see that it will show you. Well, let me start. So it's because I'm already activated. So ideally, you type activates, then dot, then you activate the environment, and then you'll be in the same position as I am. Then you press status, and then you see the other package is defined in the project.toml, which is basically like how you define the packages in your project. So at this point, the packages are not installed. So to install, you type instantiate, and then Julia will install them for you. So in my case, I already installed all the packages, so it was basically instantaneous. But if you don't have, if you haven't installed anything, then it might take a while. And that's it. Like then you're gonna have a working version. And then if you're gonna start the Jupyter, and you don't have Jupyter in your computer, you're using iJulia, which is a package that was already installed. Then you just type notebook, and then if you just start notebook, it will start a process in the root of your home. If you don't want to start in the root, you can pass the dir equals print working directory. So basically, I'm gonna start a Jupyter session inside of Jupyter. So just for demonstrations, I don't know if it works, but it should work. So it worked, and then you have the Jupyter started here, and then you would go to docs, and then you presentation. And here you go. You have the notebook started, and while it's loading, so you should see the Julia 1.6.2 as your kernel, and then you're good to go. So maybe I'll pause now and ask if anybody had any issues I can help with. So I'm gonna reserve maybe 20 minutes to help anybody with the installation. So please let me know. Maybe you can write in the chat so everybody can see, or you can unmute yourself and maybe describe your problem. Sometimes it can be difficult to write. So is everybody good with Julia? Have you been able to install?
Hi Guilherme, can you hear me?
Yeah, I can.
Here, yeah, I'm a PhD student from psychology department. I'm very new of all the programming language. So actually have a very stupid question about the installing the repository, because I'm using a Mac here, and so when I try to cloning the repository, it shows me there is a fatal error. Like, okay, let me try to do it again.
Well, you can instead of cloning, you could come here, code, and then download zip. So then you can download the repository as zip.
Yeah, I already downloaded that. Yeah.
Oh, you did? Okay.
Then after downloading, is there anything I should do after that?
Okay, maybe you can share your screen, and then we can,
Yeah,
maybe it'll be helpful to other people as well.
Yeah, sure.
So I'll stop sharing mine.
So I will share my desktop directly.
All right. Okay.
Yeah. So this is the downloading folder here.
Yeah. Okay.
And
So, all right, then you have to open a terminal. So you're familiar with the terminal?
Yeah.
Okay. So you go to that folder in the terminal. So you just type CD.
CD.
Yeah, and then space.
Yeah.
And then you have to know the path for the term. So if you you know what's the path for the term for the directory there? So if you go,
let me.
Okay. Oh, so if you can right click there, go to services.
Yeah. I think gimbal setting phone. Path is here, right? Is this
yeah. But there's an easier way. You can just right click with the PhD in the folder.
Okay.
Then go to services.
Service.
And then you can new terminal at folder.
I see.
Yeah. So there you are. So if you press LS, it will list everything.
Sorry, what should I type in here?
LS.
S.
Like this. So I put in the chat there. So letter L and S. So you should be able to.
Sorry, I cannot see the chat.
Okay, no, don't worry then. You don't need to type that. So you can start Julia straight away now. So if you delete that, it's Julia. Yeah. Okay.
Okay.
Then you can type enter. So you don't have Julia. So do you have Brew in your computer?
Yes.
Okay.
But I think I already downloaded the Julia. I don't know if I downloaded it correctly.
Oh no, that's fine. So maybe you click in Julia there.
Okay.
All right. Then if you press wait, let me see. Then actually from Julia you can go to shell mode, which is so if you press semicolon. Okay, now you're in shell mode. Then you do CD, then space, and then you have to put the path of your directory there. So it will be where it says where. Yeah, there. Yeah. And then you right click. Just right click. I think you can copy it as a path.
Okay.
Copy. Yeah, and you paste there. Yeah, then press enter.
Do I need the?
Oh yeah, you need to.
Yeah. I think. Let me try. This can work.
Yeah, and then if you just press CD and then allow, okay, press OK, and then it's CD again, and then no, CD space, and then you start writing PhD, and then tab, press tab.
Tab.
Yeah, tab is on the left side, so it auto completes the path.
But it gives me nothing.
Okay, then it's okay. Then you just write the name of the folder, I guess.
Okay.
So PhD, teach PhD.
But why I cannot move my cursor?
Just delete everything. Press backspace.
Yeah. But why is it like this? I cannot move my cursor to the place I want to go.
There's no such file. Okay. So if you write pwd. Yeah. And press enter. So that will print your because you're not. So you do change again.
Change.
No, SCD. And then space. Then type downloads. Press tab. Down, yeah. Okay, now press enter. Okay, now you type again the PhD, teach PhD.
Oh.
Okay, and now we are in the right location.
Yeah.
So you can you press backspace. Okay, now you press the right bracket.
Oh.
Yeah, now you're in the package mode. So you write instantiate. No, sorry. First you write activate, then space dot. Yeah, so that means you're activating the current directory. So press enter. Okay, now it's activated. So now you can install the packages. So to install the packages, you write instantiate.
How to spell it?
So I-N. So press tab now.
Okay.
Okay, then enter.
Here.
Okay, now it's installing everything for you.
Okay, thank you so much.
Okay, then we can after installed, then you can start the Jupyter. So that's so it's going. So we can wait, like then I can show you. Then you have a working version there.
So can I access Jupyter from here?
No, you access it from the. So you see, like if you go back to the terminal there.
Okay. Terminal.
No. You go back to where it's installing. Yeah. So let's wait for this to finish. Yeah. Okay. So it's downloading everything. So you're studying psychology. So what kind of research are you doing? Like,
yeah, I'm studying children's behavior, like their moral behaviors, lying.
Oh, okay.
Yeah. So I also don't know why I attend this workshop, because nowadays we are still using mostly the linear regressions. Yeah.
Oh, but Julia, you can. Julia is actually you can. There's a lot of statistical packages for it, like for linear regression.
Yeah. We use R mostly to do that. To do the but it's very interesting. I really enjoy your motivation for the definition of science. Yeah. It's very inspiring, and the token, the dice rolling, the token.
Oh, I'm glad you enjoyed. No, actually, like. I used to use R a lot as well, because I study economics, and then but then since I started using Julia, it has really like revolutionized the way I write. So maybe it's a good thing that you're attending the workshop, so you'll be able to learn a new language, and if you like it, I can point you to other tutorials that teach you how to do linear regressions and all that to Julia.
Yeah, thank you so much. Really appreciate it.
Yeah, you're welcome. So now what Julia is doing is pre-compiling all the packages. So because, like as I mentioned, like Julia is a just-in-time compiler. So if you were to start using a package, it has to write the machine code for this, and so that's what it's doing now. So it will be easier to start. It will be quicker to start once you start using it.
Okay. So it's like there is a package like ggplot in Julia to do visualization. Okay.
Yeah. So right now what you're doing is like you basically installing all the packages. So actually R doesn't have, like if I was teaching you R, I think it would be almost impossible for me to help you now, because like there's no way in R that you can define all your packages and then you can just install it from R. You would have to do some like some gimmicky to like get all the packages from a text file to R, and there's no environment. So I mean that's one of the benefits of Julia. So it's almost there. Some packages they take a little bit longer than others because they are larger or something, but I think you're completing it fairly quick. So if anybody else has problems, feel free to write in the chat or share. Okay. Then okay. Once it completes, let me know. Then we can. I can show you how to get the Jupyter session started. Okay.
Yeah.
All right then. Okay. Maybe I'll continue, and then you let me know once you done, and I can make sure that it's working for you.
Okay. Yeah. Thank you.
Okay. So let me go back. So right. So okay. So covered installation. Sorry. So so there's multiple ways of interacting with Julia. So today we're gonna use the Jupyter version, so number 3 here. But depending on your level of, depending on your how you like to program and your use cases, there's many different ways of using Julia. So you can use it as a script language. So if you write a script in a text file, then you can just Julia in the script and it will run. You can use the interpreter like we just demonstrated with BUA. I hope I said your name right. And then you can use iJulia, Jupyter. So that's what we're doing now. And then something that's very popular in the community is VS Code. So it's basically like if you're familiar with R and then you use RStudio, VS Code is basically, Julia for VS Code is basically the RStudio for Julia. And VS Code is just like a very powerful editor. And the Julia package is just another package for the editor. And a lot of people use it. I personally, I don't use it. I use just my terminal and bit, but I highly recommend this. All right. So another thing with Julia is that if you want to make sure that you have multi-thread support, you want to start Julia with a flag T and then say Julia T and the number of threads you want to use. So in this case, I only started with one thread because it's just for illustration purpose, but for production, for very heavy simulations, you want to make sure that you use more than one thread. Otherwise, everything that so under a lot of packages is parallelism, and if you don't use more than one thread, you're not gonna take advantage of that. So when in doubt, just pass the flag T2 for depending on how many threads are available in your computer. All right. So as I just mentioned, like Julia is so the package management for Julia is very good. Is something very unique about this language, and then you can basically browse for packages here. Julia packages. Okay, maybe it's not working at the moment. You can also check in Julia Hub. But most often you're probably gonna go to this course and type your question and see what people are using. So I covered this part, how to use the package mode. So I'm just gonna now maybe illustrate what's a package, so you have an idea of what's going on. So okay, but before I do that, so here I've shown you how the package mode works. So if you type this character here, you go to package mode. If you're writing a code in a script and you don't have access to the interpreter, of course you cannot just type the right angle bracket. You have to use the package basically. So you do import package, and then if you want to check the status, you do package.status. So if you want to activate the package, you do package.activate. So everything you can type in the package mode, you can access using the package module. So what's a package? So a package is basically a way of organizing your Julia code in a way that you can share with other people and you can install it very easily. in the basic anatomy of the package is that you have a folder. So the folder usually has the name of your package. So in this case, my first module.jl. The .jl is a Julia convention for packages. It's sort of required, but it only means that it's a directory. So it doesn't mean it's not any special type of file. And then you have like, usually you're gonna have the documentation in a folder, and then you have the source, that's where you write your code, and then you have tests, and then you define what your dependencies and your manifest. So maybe like I can show you like I show you some packages that I use. If you go to Flux, so like this would be the so this would be the Julia Hub, and then you go to the GitHub repository, and you see that the documentation is available here. And basically, usually documentation has its own projects because it has its own environment, so it doesn't get mixed up with the development environment. And then you usually go to docs table, and everything that's in doc gets compiled to this documentation page. And all the documentations like look very similar, and it will show you how to do things and all that. And then you have the source. So the source is where you define your functions, and then the point of entry for the package will be the name of the package, so flux.jl. And then you define the name of the module here, start with module flux. And then here you define all your dependencies. And then when you say export, you define everything you're exporting. And basically the way you write packages, I'll show you, is that you include everything that you've written. So with include, so it's basically like you copy and paste like all these files in this file, and Julia is basically exporting a lot of the things that you're defining. And when I mean that Julia is written in Julia, so like let's say you want to know how the chain or dense layer is written. So you probably go to layers, and then you go to like basic, and then here you go. Everything is written in Julia. How you specify a neural network chain, and how you do how it operates, and a lot of different things that I'm not going to cover. But just to show you, like, so for the dense layer, so the multi-perceptron is written in Julia. So if you ever want to know how the hell is it implemented, well, just go and read the code. I think it's a little bit different than than in Python, where like a lot of this thing is written in C. So okay, so if you want to learn more about packages, maybe this is a bit outdated now. Now the Julia Conference 2021 has a video about how to develop packages using VS Code. So if you put JuliaCon 2021, and then you'll see here package development using VS Code. So anyway. So as I mentioned, like what does a module look like? So a module is basically like so I use the Jupyter now. A module is you define module with the keyword module, and then the name of it, and what the name you want to give. Then you say using statistics, so you define what you want to what a package it depends on. So when you say using, it's basically like in Python import, and then everything that you import with the keyword using, it will import all the functions in the global scope. So as opposed to Python, where you import and then you prefix every function from that package with the package name. In Julia, no. If you say using statistics, you're gonna import everything like So for instance, the function mean is a function from statistics. It just gets imported straight away. And then here is just a little bit of gimmick from for Jupyter, but you say include, then this @dir is basically a macro for, it's basically a way of specifying your current directory. It basically knows where your current directory is, and so you include that code. So if I go and open the documentation and then example.jl is basically like a Julia script, and then basically is you say include is basically like I'm copy and pasting there, and then I can define constants. Like constants are functions that don't change. So if I say my constant equals 100, so Julia knows that it's always going to be equals to 100. So if I try to say 20, it's going to fail. Okay, it doesn't fail, but you shouldn't do it. As you said, it rates a warning. But why you want to define constants is because we're going to see Julia is based on type inference. So when you define a constant, Julia knows that that constant is of a certain type. Whereas if you just define a variable like x equals 1, Julia doesn't know what that variable is going to look like, because it could change, could get a different, it could have a different type or something like that. Okay, then I included, so include has a function called hello world, and I also add a function straight here in the module, but we usually wouldn't do that. And then I'm gonna export the 3 things from my module. So my first constant, the function hello, and then the function run on average. So somebody asked, like, can I loosely say the package is a collection of modules? Yes, you can, but there's I think there's a catch, and there is a lot of discussion there's a big discussion in discourse. What's the difference between package and module, and can I define multiple modules inside of a package? So in practice, people usually have a main module that basically exports everything they want from that package, and then if your package is too complex, you're gonna have like sub modules that basically like encapsulate very specific things that are done in your package, but you don't want to expose to external environment. In practical terms, if we're just developing a simple package, just start with one module, maybe develop everything, and then if you feel it's getting very complex, then maybe start adding sub modules. But it's not many people are using a lot of modules unless again it's very complex. So have you been able to start Jupyter? Let me know if you have any problem.
Sorry, can you teach me how to do that? Do I need to share my screen again?
Okay, maybe I'll just let's do it. Like then you can follow along. So.
Is it very interruptive for the others, or maybe we can do it during the break or something?
Maybe it will take only 5 minutes. So let's do it so you can follow along.
Yeah, thank you.
So I hope the others don't mind. And maybe if you are stuck, then you can also learn. So you can share your screen.
Yeah.
So now you press backspace. Okay, now you type using iJulia.
iJulia.
Yeah, maybe backspace. I with the I and J capital. Then press tab. Press tab.
Okay.
Oh yeah. Okay. Then enter. Okay. Now you just press notebook. Write notebook. Yeah. Then press tab. No, notebook, and then close parentheses.
Sorry, notebook. Then.
And then open and close the parentheses.
Oh.
It's like you're calling a function. Yeah. And then close. No, parentheses. Yeah, then close. Okay, yeah. Type, then press enter. So you're calling the function notebook.
I see.
And then press Y. So you just have Julia installing the Jupyter. So let me know once this is done. Hopefully it works, and then I can help.
Yeah, sure.
Okay, so
thank you.
Okay, so going back here. So as again, as I said, if you say using statistics, you go you have a mean, it imports the function mean, and then you can just type mean, right? So here you can also use when you say import, you basically doing in Python, so you have to prefix with the package name. And here, because I'm importing, so when you're in interactive section, you basically inside a module called main, and then because I define my module inside of main, the main module, I have to import it with import main dots my first module. So it's a little bit so maybe it goes to answer Andy Gross' question. So basically, I'm defining a module inside of a module. And then I can go and call the function hello from my first module, and then I can print the constant that's in defined, and notice that everything is prefixed. So in Julia, every time I use this, so if I have a string and then I say hello, and then I wanna interpolate a variable. So I use the dollar mark, open close parentheses, and then I just type the name of the variable. So my constant. So it will interpolate the constant. Okay, so if you're looking for help in Julia, you in the Jupyter or in Jupyter Notebook, you just type interrogation mark and then the name of the function. So if I see interrogation mark mean, we'll just show you. And so there's many. So when you read in the documentation, you wanna look at the examples. You're gonna see something like this mean f function. So because of multiple dispatches, you're gonna see later. This function mean works only when the object is a function, whereas in other cases like mean abstract array, then the function works on an array. So, but the way you call the function mean is always the same. So all right, so here you press so hello true, and then because of multiple dispatch, sometimes you don't know where the function is coming from. So you use this function, this is called a macro, and then you ask which hello true, and then it will tell you that it's coming from this part, this location here. So if I say which mean 10, and you basically say where the function is coming from. So in this case, it's coming from Julia standard library, the statistics package source. So Julia actually the Julia language is has a lot of standard packages. So if I go here and I go to the source, and then so if I go to standard actually, so go to standard library. So the standard libraries that come with Julia basically defines a lot of different packages. So in that case, we're looking at the statistics package. Okay, it doesn't seem to be here. Let's see here. Okay. Okay. Well, I probably have to dig in a little bit more, but that's the idea. The packages are defined inside of Julia. They're probably coming from outside. So in any case, there is where you define. So if I'm gonna open a terminal here, and then I'll show you what I mean. So if I go Julia, and then using statistics, and then I say reach mean 10, 11. So I see that here I have the. So let's say I want to look at the code, so I can type the macro edit, and then actually I just go here which, and then I can change this for edit. And basically I open the code exactly where the mean definition is. So as you can see, it's defined on this file, which is located in the standard library inside of the statistics package. In basically every single statistics function is defined in one single file. And so you can see like that the mean function is defined as so the mean of an iterator is this, and then you can look at how the mean is calculated. So basically like here you have the definition of the mean. It's basically a loop that goes over your array, and then it adds and then divide by the count. So it becomes very easy to like code. And let's say you want to modify this statistics package. So here I am in the package mode, and then I go dev statistics. And then basically it's updating the registry. Oh, okay, sorry. I have to be inside of a package. So if I go to any. So if I go to my QE, I was using Julia. So if I go that statistics, sorry, I have I don't know how to type statistics. Okay, that. So at the moment. So I would add the package to my repository. Then it's compiling everything again. So I'll go back to it once it's compiled. Then we can continue there. Yes, so I'm modifying the standard module. I was just showing you like how to do it if you wanted, but. No, you don't need to modify it. It's just an example of how easy it is to do that. But maybe I'm overreaching. I'm overcomplicating. Like I do that sometimes for libraries that I'm learning, and I want to add a print function here and there. So I will modify that package. I just write prints in certain places, and then I can understand how it's working. But in most cases, I just use whatever. I just use how it is. So in any case. So sometimes you can define a function because with the multiple dispatch, a function can define many times. So if you want to see all the methods that are associated with a function, you just type methods, and then you print out the methods. And then finally, if you don't want to open the editor, you can type. Okay. Sorry, and then you can type less and edit are the same thing, but the less will print it in your terminal, whereas the edit will open. All right, so now we start with the tutorial of like how to manipulate objects in Julia. So it's not very different from other languages. So if we start with so maybe I'll give a pause because it's 11 o'clock. Then we'll go back. I will go through the whole Julia tutorial, and then we're gonna have a pause for lunch. And then after lunch, we're gonna dive into the ODE and all that. Does it sound good? So maybe we'll reconvene at 11:05. And please write in the chat if you have any questions, and if you have trouble. I can see B was able to load it, so I'm glad that it's working for you. and I'm glad to be able to follow it. So I'll see you at 5 minutes. Okay, so we're back. So I'll cover now the Julia part. So the way so some of the objects in Julia are arrays. So you can define a column vector like that. If you want to avoid the line breaks, you can use the same column like this. So in Julia, as opposed to Python, index start at 1. So make sure that you don't do something like this, b0. So it's sometimes important to sometimes you want to initialize a vector, but you don't know what's going to be inside of the vector yet. So it's a good thing to do that when you're doing like a lot of operations that you basically want to initialize a vector, do some operation in it, and then get the results, then do similar operation on the same vector, and then before you start the loop, you just want to have the vector ready. So here you say vector. Vector is a type of object. Then what type of vector is it? So the float 64. And then undefined is just a way of saying it can be anything for now. And then 3 is the length. So if I do, like, for instance, vector int 64, so integers, and then I give 4. So I basically generate a vector with random numbers that will be populated later. And that's exactly what I'm doing. So like I say b1 equals b2 equals b3 that equals 5. So as opposed to a vector, we could have a row vector. So that's the way you define it. Just put the numbers separated by a space. And in that case, we create a matrix of dimensions 1 by 5. A vector is basically the subtype of a matrix. So you can see, like, so if I type what's the type of B, sorry, so what's the type of B, you tell me it's a vector, and then this will say that this is basically saying is a subtype of matrix floats 64. False. Okay, so maybe it's the other way around. Okay, anyway, no, okay, so they're not subtypes of each other, but a vector is a type of array, which I guess is not a type of a matrix. So I could transform a vector into an array by saying matrix. Okay, I cannot. Anyway, I have examples down there. So B is a matrix now. So if I change the type of B, now I have a matrix. Let's say I would like to generate a vector that is similar to B. So I'll use the term similar. A will be initialized with anything really. So here notice that B is an integer because 1, 2, 3, 4, 5 are integers. So Julia realized that there is no other type of numbers in it. So they just went with the tighter possible type, which is the integer. So when I create the vector A, I want a vector that has the same dimension as B but can have anything in it. So I use similar. It's very useful because sometimes you define a function and you don't know what type of the function, what type of object the user is going to pass, and yet you need to operate on a similar vector. So you just start it with similar. So the way to define a matrix is basically like you do in math. So you just say matrix and then 1, 2, 3, 4. So notice that it's different from Python. In Python, you would add this, but not in Julia. And also notice that I'm using like so space means that you're separating the columns, and then the line breaks is the rows. Alternatively, if you just want to define it in one line, you use the semicolon for the line break. inside of line breaks. Sometimes it can be a bit confusing to figure out all this like line break space. So to be honest, for me, a lot of the times it's a little bit of like try and error, especially when it comes to plotting. If you don't pass like a vector, your plotting doesn't work. So, but at the same time, it's quite useful because you don't need to add a lot of brackets and all that. So if you want to change an element of a matrix, you do like that. And because the matrix is an integer, you of course cannot insert a float in it. So a good idea, like if you're familiar with TensorFlow, it's to know exactly what type of objects you're going to be manipulating with. So that makes code more efficient and that saves time. If you don't know what your code is going to be, don't worry. If you just want to try something quick, just make sure that when you initialize, like let's say a matrix, you just put one number as a float. And then it will change the type of the matrix to float. Okay. And then like, so here I'm again initialize the matrix, and then the way, so if you want to populate the elements inside of the matrix, you would use the notation column. That means that I'm referring to everything inside of the matrix, and then I'm adding random numbers inside of it. So now if I type A, you have A. So the nice thing about Julia that I haven't seen in other places before is that you can use this function called view. So when I write at something, it's a special way of like, it's a special type of function that I'm going to talk about called a macro. And basically this function, basically what I'm now doing is like I'm creating a pointer to the fourth row of A. So you can see that the fourth row here starts with 0.62, 0.04, and that's exactly what I have here. So if I modify A and I add, so let me do like, for instance, if I say A1 equals 10, okay, and then I look at 10 and then add A again, then you see you have the number 10 there. So here I'm modifying everything. So here you go. And an array can have, and if you define a vector with anything, so it's a little bit like in Python. I could have like the first element of the vector being 4, 5, and then these could even have strings, or like, so I kind of have like 8 yes. Okay, it has to be, because I said it's a vector of vector, so I'd have to have like this. So there you go. Like it might be a bit you might think it's a bit constraining, but you can also, it starts a vector like this, like just with random, with anything you want really. And then it will be like as any other vector. So however you prefer, then you can see that the vector of any, so a vector of anything. So how it can operate on arrays, you can use a map. So you broadcast the function x squared. Here I define an anonymous function, so it goes from x maps to x squared. So b, remember that b was 1, 2, 3, 4, 5. So now I'm like basically squaring every element. We can achieve this with there's a function called broadcast. So you say so Julia, when I square a number, you do like that. So in every function, so if I say every function is defined like so as the following. So plus minus. So is the function parenthesis expects one element x and another element y. So when I use the broadcast function, I define a function and then 2 terms, so the x and y. So in Julia, a good way of doing, Julia provides the dot syntax. So every time I do, so if I do b to the power of 3, it's not gonna work. So I'm gonna complain that there's not a matrix because vectors cannot be squared. But if I add the dot before the operator, it's basically saying apply this function to each element of the vector, and then I can do that. And anything you can apply the dot operator to anything. So if I say I don't know, like if I say if p3, I guess. So okay, so if I come and say I want to divide b by each element of b by 3, so div dot p3, and then you can also allocate using this. So instead of writing b equals 10, so you would have to add the dot. Then if you have the dots, you don't even need that one. So I can add 5. There you go. Okay, so you can do matrix multiplication normally. So you have A and B, and then you have, of course, you have to because B is a row, you have to transpose it. So like in mathematics, you usually use the prime to indicate transpose. So here you have A times B prime, and there you go. It's a matrix multiplication. So if I do A times B, it's not gonna work. And then I can also broadcast. So if I want to multiply each, so I guess if I want to multiply each row of A by B, so you use the dots. So because the B is a row matrix, so if I do 1, 2, 3, 4, 5. I'm not. So if I do times B here, so you see every row is multiplied by. So the first row by 1, the second row by 2, and so on and so forth. Or no, actually, is the first column by 1, then the second column by 2. So there's a problem with broadcasting. Sometimes you kind of have to figure out how the operation is being broadcast. All right. I mean, I'm sure it's specified somewhere, but I don't know. Sometimes I get sometimes I don't know, and then I'll test and then I'll make sure that it's the way I expect. Okay. So as I explained, and then if you do b equals 2, you're basically allocating the number 2 to b. So if b was a matrix before, now it's going to be a number. So be careful, because sometimes you might write, you might be writing a function, and then you do like something b equals 1, 2, 3, 4, 6, and then you think you're like allocating the vector to b, but actually you're creating a new vector. So that can actually create a lot of slow down, or even like create some problems in your code. So if I do like b equals 2, so when I put the same column, it means that the result doesn't get printed. So now b is a number. So there's a control flow. So you start with a for and with an and. You can have while, everything always ends with and. So the indentation is really like a syntactic sugar. You can have it with and without indentation. And show here, basically it's a macro that will print the value of the variable. So you can either have show or print. So the thing is that, like, for instance, when you define a loop, and the variable only exists inside of the loop. So the scope of the loop is the variable doesn't get transmitted to the global scope. So as you can see, it doesn't. If you try to call t, so how would you, if you wanna allocate something, you would first have to define it. So that's why so maybe you start with 0 or something, and then I don't know, in this case, like maybe string, and then now it exists. So just be careful. Be careful. I mean, our code is not going to work otherwise. And then also the I here doesn't exist. So if I say show I, but then again, if I put I equals 2, for instance, or anything really, like, and then I go show I, well, you see, it didn't change. So again, be careful, like, not to rely on using, like, in Python, sometimes use like the iterator, and then maybe you end up with number 10, and then you use I, it's 10 now. It doesn't work. And then here you have like nested loops. So that's quite convenient. So the way to define functions in Julia is pretty simple. You can either define as you would define in mathematics, so fx equals 2x squared plus 2x. And then you can use the package for diff so that when I talk about automatic differentiation, it's exactly that. It's like you can take the derivative just by calling the function. And forward diff means if you stay until the end, I'll talk about the different ways of taking derivative. But here you're taking the derivative that we know, like you compute, like basically you're computing 2x squared, so it will be 4x plus 2. So then this will be equal to 10, and then that's what's being calculated here. So in Julia we can use Unicode variables. So if you do delta, press tab. So it's very convenient. So in this case, I define a function delta fx that takes the derivative of my function f, and then add the value x. So we can define functions that modify the input. So when we do that, it's a convention, not a requirement, that we use bank. Bank doesn't mean anything. It doesn't modify the function anyway. It's just like just a string. So in this case, but it's a convention. Like every time that the developer writes function bank, it tells the user that it's going to modify the input. So in this case, I'm modifying the second elements of the vector x. And then here you go. So I think you've probably seen a lot of examples of both dispatch, but now I'm just gonna like formally introduce you to the concept. So here, like when I first defined my first module here, so actually here, when I said hello world, so the world, the first function here is can be anything, like the inputs. So if I start hello and I give with any inputs and Julia, and I didn't define a specific function for it, Julia will write hello world. If like the function type is of a number, then hello will print something else, like hello don't be full. And then this is exactly what's happening here. So we get my first module hello, then I pass an array, so it knows what to do. So it will print for each element of the array, will print the hello function. So it's pretty convenient because now I'm passing an array with numbers, numbers and strings, and then also an array. And then Julia basically like figures out like what to print. So it's printing the name here, then here's the number, then here it figures out it's an array, so it will call this function. And then for each element of the array, it will call the other functions. So this is a major feature of Julia. So it doesn't incur a lot of overhead. So multiple dispatch is really fast. So if you know how to use it well, you can use it to your advantage. But of course, it's a good way not to abuse. And here there's a discussion of performance and how to avoid how to avoid some mistakes. All right. So, and the nice thing also about multiple dispatch is like, let's say like you define you can also like modify functions, like so you import base and then you can modify like base plus, for instance. So if you have an object, you modify. I'm gonna show it later. Okay, so another thing about Julia is that like it's known to be fast, but what we mean by that, like in Python, people always say you have to vectorize your operations. So if you're multiplying two vectors, make sure you don't write a loop. Use numpy just multiply the vectors every time you think like how can I vectorize this and that. In Julia, on the other hand, vectorization does not necessarily improve performance because all the code is compiled in C. And in fact, in Python, when you vectorize an operation, you're basically like dispatching into a code that has been written in C, and that code, of course, will run that loop with because I mean most implementations of vector operations you need to have a loop, like otherwise it's impossible to multiply. Otherwise, there's some clever way, but in most implementations it's a loop. So here I define I will create two vectors with random numbers inside. So if I can show you, like A is a matrix of random numbers, and then I use something that's very convenient library in Julia called benchmark tools. So every time you're developing code, you want to know if your code is efficient and all that, you can use this package for computing benchmark. So in Julia, arrays are column major. So what do I mean by that is that like so Julia will store so when I vectorize the matrix, so if I type A column, it will show the matrix in vector form. So this is equivalent to writing back A. So basically like if you look at A, so A starts with 0.685, then 0.67. And when it's vectorized, it's basically like you start descending the first column, then you go back to the second. If it was row vectorized, you would go 0.685, 0.53. So you go that way. So in Python, the matrix are row major order, but in Julia, they're column major. It's important to keep this in mind when you're like writing code and you want to make sure that it's fast. So any operation that you can do in column major form will be faster. Now I'll just show you an example. So here you run the benchmark with the B time. So it will take a while because B time is basically not a while, but like a few seconds. B time is basically running the same function over and over and over again to compute an average of like how long it takes. So here what's happening is like I define a function that takes that modifies the vector C, and it takes as input the matrix A and B, and it only modifies the ith row. So I come here and then I use a broadcasting operator to modify the ith row as the as the product of the i's row and the b's row. So it's just hypothetically. And then I use b time, and I set it up with matrix C, which is started as undefined, and then I modify the second row. So the output says that the code took 19 microseconds to run and use 2 memory allocations. So I'll show you that it's actually possible to reduce the speed of this code significantly and also use no allocation, which is great because if you're writing code that that operates on very large objects, then you don't want to be cloning cloning objects and all that. So in order to compare the row and the column major, so this so here I'm modifying every row, and now I'm gonna modify a column, and then as you can see, I'm pretty much doing the same thing, but now I'm modifying a column. Rather than using the dot operator, dot equal and dot times, I can use the macro adds dot, and basically what I'm doing is the macro basically rewrites this expression as this with the dots. So here I perform a column major operation, and the operation takes only 1.8 microseconds, so like it's 20 times faster. So that's important to take into account. I mean, if you're just writing some code to test ideas and all that, it's like you don't need to optimize your code straight away. But once you figure out what you want to do, and maybe you want to run a lot of simulations, and this is usually done when you're dealing with ODS, you usually want to run your code multiple times. You're looking for a solution, you need to run your law of motion multiple times. So you want to make sure the code is somehow optimized. But don't try very hard. Like if it doesn't work and you're just playing out, it's okay. You shouldn't waste so much time. So the second way I modify the function is so the second way I modify the function is like, instead of like here, what I'm doing is like I'm creating 2 vectors. I'm creating a vector that I create a vector that's the multiplication of A with B, and I'm taking that vector and then I'm creating and I'm allocating to memory, and then I take that vector and allocate to C. So I create 2 allocations. But we don't need to do in theory. You don't need to do any allocation, because I could just do the operation and directly place it in the place where I want it to be, so in C. So rather than multiplying in a temporary vector and then allocating it to my final location, let's just put it straight where it should go. So that's when I use the view macro that I showed you before. So basically every operation in this function will so I'm saying like, okay, this function will operate, every vector operation of this function is a view. So when I say ci dot, I'm operating on a pointer to that matrix. So here I do that, and as you can see, the code takes a little bit less time, but the good thing is that it does not allocate any memory. And then the major difference really is if you do the column operation, you see significant reduction in time. So it was 1.8, and here was like only the nanosecond scale. So nanosecond is, so I think 1 microsecond is 100 nanoseconds or something. So yeah, so 1,000. So you see it's like major improvement. So yeah, it's so what's going on under the hood? We can always look at the so when I said that the Julia is precompiled, basically like you write the code in Julia, then it's precompiled using the LVM compiler, which also compiles C code and all that. So if you developing code and you're getting into very technical details and you want to see how your code is compiled, you can just use the code LLVM, and then it will show you the machine code. And there's variations of this. So if you want to see the code in just as so first you do 2 times 4, then Julia will compile this code to the lowered version, and then after to the LLVM, then after it will go to the LLVM compiler, and then after you write it into machine code. So using code native, you can see how it's implemented in your machine. I mean, this is very useful if you're doing very advanced, if you're doing a lot of numerical, numerical programming, and you want to optimize your code, and you want to see what's going on under the hood. That's a good way to do it, and it's something that's not available in Python. So I mean, probably it is some. Probably you would have to, because the Python code is sent to the Python to the Python dynamic executor. So you have to know how the dynamic executor compiles the code and all that. Whereas in Julia, like every single line is compiled directly into LLVM. Okay, so I claim that vectorized code is better. Vectorized code is not necessarily better than loops. Okay, so I have to demonstrate that. So here I'm gonna perform the same operation, but modify by using a loop. So let's see what happens. So here I don't need to use a view, because basically I'm operating on every single elements of the matrix, so it doesn't cause any allocation. Whereas here, because I'm doing a vector operation, I have to kind of tell Julia, look, you can just use a view. So important to keep this in mind. If you're just doing an element by element operation, because these are like this basically numbers, you don't need to use views. And then you might find surprising, oh, you said that loops are faster, but I can see here that the broadcast operation takes 113 nanoseconds, whereas the loop version takes 820 seconds. Okay, so something that Julia is doing here is like for every iteration, it's actually checking if like the j, so the index j is within the bounds of the vector. So that's an operation that takes time. It's safe, but takes time. So if you know that your loop is not gonna advance anywhere beyond the bounds of the object, so you want to use a macro called inbounds, and you tell Julia, I'm not gonna modify anything outside of the memory, outside the memory allocated to the matrix. So every index j is inside of this matrix. So again, so if I run this code and I time it, I will finally see that the code takes much less time. So here it took 113 nanoseconds, and now I have 90 nanoseconds. So okay, so the significant improvement from the original naive operation. It took 1.8 microseconds, and even from the vectorized version. So 113 nanoseconds versus 19 nanoseconds. So my claim is that like Julia is good, because you don't need to think all the time about, do I have to vectorize this? Do I need? In most cases, like if you vectorize, your code will run fast. If you use a loop and then if you use a loop and you don't need to check for the bounds of the memory, your code can even run a bit faster, but it's not that much. But maybe if your matrix is really large or something, maybe you have like significant improvements. But here it's maybe like only 40 nanoseconds. So I mean, it's considerable, but not that much. And then there's packages that try to like turbocharge the vectorize operations. So one such package is the loop vectorization. And then in this case, I use the macro turbo, and then and you see that the broadcast operation then is even faster than the. So in summary, like there's many ways that you can optimize your code. Don't over optimize it in the beginning. It's good that you are aware of all these options, and don't be afraid of using loops. So if you're coming from Python, that might seem like a sin or something very wrong, but just relax and use loop as you want. So just cover some of the basic types. So numbers in Julia comes in many types. So you have integers, floats, 64. Next thing you have rational numbers. So when you do, so if you do like 1 divided by 1 is a normal division. If you do 1 divided by 2 with double 2, then it's a rational number. So it's a fraction. And then of course you can add fractions together. So if I do, so you get the fractions. And then if you write 1F0, so the F0 stands for float 32. Yeah. So there's a very convenient notation for float 32 because if you're familiar with machine learning, a lot of the code that is that's executed in GPUs are better optimized with float 32. So if you're sending any code to the GPU, you might want to use float 32. Then you also have tuples, and then you cannot modify tuples. You have dictionaries. So for dictionaries, you use this funny looking operator, the arrow, and then you have like the column D stands for symbol. So it's not a string, it's a symbol. So it's like, so we humans read it as a string, but the computer reads it as like as an ID. Like so, dot column D would be allocated an ID, like let's say 15. So like if you're accessing that, it's very much faster. So you see the blue, T-ball. And then in this case, I allocated 45 to this, which was 2, now it's 45. So what is this column here is a symbol. Symbols are a way in which the language can represent itself as a data structure. So I'm basically saying like, when I evaluate D in the global scope, so D here is in the global scope is a dictionary. So I evaluate it in the global scope and gives me the dictionary D. But when I evaluate the symbol D inside of the dictionary, it's actually a key. It's a key of the dictionary. So it's evaluated in that scope and then gives me the value. So that gives you some idea of what symbols are for. Then you have iterators. So actually, like you can define an iterator for a very large number, and then Julia does not store every single number of the iterator, like, but it stores like the start and the beginning. So if you look at the field names, it has start stop, and I'm just gonna. So if I say 1, 2, 4, and then collect is a way of producing an array from the iterator. So I end up with like 1, 2, 3, 4, 4. So okay. Okay, and then now types. So Julia doesn't have objects like the way it has in Python. So you cannot define like an object and define methods for that object. So it works a little bit different. So you can have types. Types are just a way of like holding data. But you don't go and then define like a method for that. So you define you specify a method that works for that type. So use multiple dispatch. So it might feel similar to Python in that sense, because like you can define a method for every type, but actually but actually it's not quite the same thing. So you can define immutable types. So in this case, I define a point. So X and Y are the data inside of the point, and then to initiate the structure that I just defined, I just call it with the input. You cannot mutate the types, so immutable types. So if I try to change the X, it's gonna give me an error. Now for mutable types, I can change the input. So if I say px, will change. So it's very important to think about what you're going to use a type for. So immutable types are of course always much more efficient, much faster, because like you there's a technical term like immutable types, it's heap allocated, so you have to look in the memory and then like you have to get it from, whereas immutable types are stored closer to the CPU, and so they have a much lower memory access, so they're like stack allocated. And finally, like if you want to define an abstract type, so abstract type is just an umbrella term for like you cannot define any data inside of an abstract type. It's more like an umbrella. Just say like I'm gonna collect all types within this umbrella. So here I'm saying abstract shape. There's also like number. Number is an abstract type. So if I say like is inch 64 a type of number, and I say yes. So this symbol here means like is it a type, subtype of. So all right, and then of course like I can say methods with number will give me all the methods with the use number. So it will be a lot of methods, and hopefully the computer is not gonna freeze. And maybe I did the wrong thing. Anyway, while it's doing it, we'll continue. So I define a structure for the square, the abstract shape. Okay, here you go. So everything that defines a method for a number, it's here, which you see is a lot. 2,217 methods. All right, then I can define square as a type of abstract shape, and then it has a coordinate and a length. So now be aware that you cannot redefine structure. So once you define it, you cannot redefine it. Here it works because I'm basically defining the same thing. But if I was to modify the square to something else, it would fail. And then I can also define a type that for which the elements inside of it are of some type. So in this case, I say the rectangle whose elements are of subtype T, and T must be a subtype of number. So in this case, X must be of type T, which is a subtype of number, and Y must be a subtype of T, which is Y must be a type of T, which is a number. So this is very convenient for writing very generic objects that will take different types of numbers, and then every time if you define methods that operate in a certain type, your code will be more efficient. So then I can, as I mentioned before, like we can redefine, for instance, the operator plus addition to work on types point. So what I'm doing, so when I'm redefining any operator in the base package, I have to prefix with base. So I'm saying base plus, and so the addition it adds all the coordinates x and the coordinate y and give me a new point. So that's what I do. Okay, so one final section before we break for lunch is meta programming. So you might have seen a lot of these commands, the macro that I mentioned before. So macros is basically like a function that writes a new function, writes a new statement. So in Python you don't have this, but there's other languages you have, like so certain languages allow you to rewrite the language itself. So with a macro, I'm basically like passing inputs, and then that input is used to write a new expression, and I get back the expression. And when I'm using a macro, that expression gets evaluated straight away. So we can, as an example, so I define a macro with the macro keyword, and then the name of the function, print ln, and then s is the input, so it will be a string, but can be anything because I didn't define. If I want it to be a string, I'll say string. So like if you want to say the input can be anything, you could write s column any, but you can also just don't write anything and it means the same. So basically what I'm saying is like this function will return an expression. So everything inside of this funny looking brackets that starts with a colon and parenthesis and then ends with a parenthesis, everything inside of it is an expression. So I'm saying like I'm gonna return an expression that reads like print ln, and then when I use the $, it means that I'm replacing the $, with my input s. So it's a little bit like when I write full a. So I'm replacing a with whatever is in a. So here, because I'm writing an expression is nothing more than a special type of string. So here I'm just like print ln, then substitute the input for this for the $. So what I end up basically is, so if I say print hello world, it returns me this expression here, print hello world. It returns me this, and then because I'm calling as a macro, it gets evaluated straight away and prints the hello world. So it's basically doing this. So when I write print ln, so I can also do like print ln hello world. You can also call it as a function like this. So yeah, that's pretty much the idea of macros. And maybe don't get caught up. It's not necessarily to understand how to write macros, but it's good to know like that they exist because they come up every time and everywhere, and it's just good to have a basic understanding how they work. So I hope I provided this. I hope you can understand it a bit better now. And there is Julia Kohn also has talk about macros. So yeah, please feel free to watch it if you want to know more about it. And here I've listed a few of my favorite tutorials. So with the conference going on this week, there's even more tutorials. But I put this list together before the conference. So of course there's the Julia documentation. And then all the documentation kind of look the same. This is the standard library. So you want to go here, and then maybe if you want to know how linear algebra function works, you have everything defined here. So for instance, the identity matrix in Julia is defined with this funny looking. Is defined with the I symbol, so I, and then you can read more about it. Here. And the nice thing about the identity in Julia is that like it's actually not a matrix. It's just like a smart way of telling the code that I'm multiplying and the operation related. So here there's official recommendations and also like pointers to more tutorials. And then like there's like some quick tutorials as a cheat sheet. So in case like you want to just remind yourself of like some of the operations. Also like you can compare like with Python, and then like here it shows you like the difference like. Actually numerical, and then it shows like MATLAB, Python, Julia, and then you can compare. So a very nice course also if you want to get very deep into the numerical programming is the MIT course from Chris Rakaukas. And this one goes very deep into how to optimize your code, how to do like automatic differentiation works. And how to do and how basically is a very good next step if you wanna go even deeper to scientific machine learning. Now, if you wanna maybe go a different direction, or you just want to get more exposed to Julia. Sorry. Okay. I'm sorry. Maybe I have to. Didn't fix the link. I'll fix it. So here MIT also has put a course, Introduction to Computational Thinking. It has very good materials. It's written in a different type of notebook called Pluto, which is only available for Julia, which is basically like an interactive notebook, and then like you can watch the videos here, and then you can like follow along. So if you click here in Editor Run this notebook, you actually are gonna have an interactive notebook right there. So like we're talking about ODs, you know, like so you can watch the lecture, and then you can basically go to run it in your computer. Maybe I'll load it, and then we can go back to it later. So I can show you also another feature of Julia, which is Pluto. Anyhow, this completes the tutorial for Julia, and then we're gonna have a lunch break. So I propose that we have an hour. Let's see, now it's 12. So 1 hour of lunch, and then we'll come back here at 1 o'clock, and then we then dive into the ODs that I spoke at the beginning of the course, and tell you how to solve ODs with Julia and neuro ODs and all that. But before we go, like maybe would you like to ask any question? Maybe give some feedback. Am I going too fast? Am I going too slow? Is it the right speed? So if you please feel free to share any insights that you had so far.
Yeah, sorry, can I have a question?
Yeah.
So regarding the last part of macros, I'm not sure that I got the idea. Is it the same as just to call the programs or script from the terminal, or there is some additional functionality?
Yeah, so macro is basically yeah, it's like just writing code basically, but because when you write code, you have to specify everything when you like maybe when you write a code in your terminal or in your editor, if you say like x plus 1, and then you say print something, you have to write what it is that you want to print, and you need to define x, and say x equals 10. But when you're writing macro, you're basically saying like, I don't know what x is gonna be. I just want to let I'm just gonna say like the user is gonna specify x, and then when they call the macro, x will be we'll substitute x for a value like let's say 10. And so like it's basically a way that I'm writing code about code. And this is very convenient because Julia is compiled, it's just in time compiled. That means that like there is actually like there's a way of defining a type, like let's say enumerates type, and then I say SIR for instance, and then it creates a type of S, creates a type of I, and a type of R, and then if I took S here. So it's an enumerate type, and then it assigns a number to it. So actually, like it's so if I say s equals 0, it's false. So no. So the type. So I define a type called s, and inside of that type it has like it defines two subtypes. It defines two variables I and R. So if I say I equals 0, then I get. Sorry, I'm getting something wrong. So I have to go back to it. I was using it the other day, but I think
Maybe could you define s dot I equal to 0? Will it work?
No. So the idea is like so now you have I is basically like is a type of type S, and that I equals to 0. So for some reason it should be true here, but it's not. So if I say methods with I, it also defines methods. Oh, sorry, methods with S.
Okay,
So,
talking about like if we compare, like I could create a function, right? That should take some inputs, like ordinary function.
yeah.
And what's the additional functionality of macro comparing with just creating like a function with conventional inputs?
Yeah. So
is there any like particular example? Yeah, when you like when it is not the same.
Yeah. So yeah, one example is using this enumerate type that I didn't quite demonstrate the utility here, but the idea is like you want to have like so in this case you want to have like you want to have types types of type S, so within an umbrella, and then you have type equals, then I represents 0 and R represents 1. Another example is like the show, for instance, show I A. So it's a way like of printing the code, and then you wanna pass this. Also, like if you go to the plots package, so you can actually define recipes for plotting. Sorry. And then when you define these recipes, you basically like plots. So let me open here.
So actually, you could write a script that will modify the code for let's say for each instance.
Yeah. So for instance, like here for plotting, you can define a recipe using the macro recipe, and then you're basically like telling the package how you want to plot something. But because like things might change, like the value of X and Y will change, and then the type, and then you want to define a recipe for a certain type. So in this case, it's like you want to define a type of histogram recipe, and then the macro will allow you to like write a generic code, and then when you call the macro, so when you call the recipe, so when you call the recipe, it creates like all these functions. So marginal hist. So here you want to define you have a recipe, a macro recipe that defines that will write a function for plotting marginal histograms. So basically you pass the body of the function, and what this macro is doing is taking this information and rewriting multiple functions in your scope. So one of the functions is the function marginal hist. So notice that here in the recipe, you didn't define the function marginal hist. You just define like a few, you tell the plots the type of things that the marginal histogram must have. And then basically the macro is then rewriting, it's taking that information and writing a script of how you define the function marginal histogram. And then it's also like defining like the type marginal histogram and all sort of things. So it's basically like taking an input from the user and rewriting a script based on that input without the user needing to write a new script for every modification. But I think it sounds a little bit convoluted, but
do you personally use it? Because it sounds like if you like maybe like every problem like that, if you think a little bit, maybe you could write the script that not needed to be like modified at the time. Do you personally find like?
Yeah, like I use it a lot for plotting. Sometimes I use it for plotting. So
sounds like the plotting is a good example. Yeah.
So so if I'm working with some data and I'm always gonna plot, but I want to modify some certain things, then I'll use it for plotting. I can show you an example after lunch. But I would say this is more of an advanced feature, and I usually use macros that are defined by a package, and then they will tell me like this is how you use the macro, that I use it. But most of the cases is a way of optimizing the code such that it gets compiled in a certain way that's more efficient. And I think you're only going to understand that once you are more advanced with the language, and then you come up with a use case. But otherwise, I don't really use a lot because I'm not that advanced, I think, with the language.
Okay, thanks. I got an idea.
Yeah. All right. Any other questions or comments? All right, then, so let's pause for lunch and then we'll come back to the second part of the course after lunch. So now it's 12:05, so we come back at 1:05. So yeah, have a good lunch.